Live from YouTube, welcome to the Chicago Python User Group's main meeting for August 12th, 2021. My name is Joe Jasinski. I will be the MC for tonight. And our meetings are held the second Thursday of each month. Before we get started, oops, I'm not sharing my screen here. Before we get started, I'd like to just mention our code of conduct, which is how we expect people to treat each other in real life and online. So please check that out on our website and abide by that and just treat each other with respect. So what is ChiPy? ChiPy, or the Chicago Python User Group, is a Python-focused community started in 2003, and we started it meeting in the back of a bar and have grown to be a very large Python community with lots of online communities and resources. ChiPy is made possible by our board members and by all of our organizers. So we have a lot going on, and ChiPy wouldn't be possible without all the volunteers who help out. So a big thank you to them for all the work that they do. ChiPy has a number of initiatives. We have the Python Project Night, which is a space for people to get together. Right now it's a virtual space for people to get together and work on projects. The Buddy Mentorship Program, which is a tool to help you match mentors and mentees together. The Python Lunch Break, which is basically ChiPy at lunch. And we have a ChiPy job board, which lets you search for jobs online on our chipy.org website. Here's our special interest groups. We have finance, data, web dev, DevOps, algorithms, and newly the entrepreneur SIG. So you can check out our meetup page to find out more information about when the next meetings are upcoming. Speaking of which, we have a few upcoming meetings. We have a meeting of the Data SIG on August 19th, the Algorithm SIG on September 2nd, and the next main meeting will be September 9th. Some Python news. Interesting this month, Jupyter, or VS Code, just updated their Jupyter Notebook support. This is very cool. Lets you run Jupyter Notebooks inside of VS Code. This has been a feature that's been kind of in development and kind of an alpha state for the last year or so, but this month they made it more official and really made a nice integration. You should check it out. It's really cool. Also, the PyCon US 2021 talks videos are available at the following links. So check out the YouTube channel for PyCon. We have some great talks planned for tonight. I'm looking forward to them. So stay tuned in just a minute. We'll have those talks upcoming. To participate in the chat and ask questions of the speakers, you can use the chat box on YouTube. So say something, say hi, and to get us the conversation starter, why don't you tell us if you've heard of any awesome Python news for tonight? So after the meetup, we're going to be having a Gather Town meetup at the website chipy.town. Gather.town, if you're not familiar, is a interface where you can kind of meet in virtual space and chat and get to know each other. It's a replacement for in-person until we get that working again. You can find us on Slack at join ChiPy Slack at herokuapp.com and on our Twitter account at ChicagoPython. And finally, you can find out all of this information and more at our website at chipy.org. So please visit that for more information. So this takes us to tonight's meeting. And let me introduce our first speaker. So Zack, welcome to the stream.
Thanks for having me, Joe.
Thanks for being here. Zack is you may or may not know is our the ChiPy chair, and he's going to be talking tonight about a really interesting topic. But before we get into that, Zack, tell us a little bit about your background in programming.
Yeah, so it all started actually at ChiPy, kind of for me. So I worked in finance in a non-programming role a number of years back, and just started attending ChiPy, got interested in programming, self-taught for the most part up until joining the ChiPy's mentorship program as a mentee on my second try a few years back. Did a cool data science project, and that broke me into data science professionally, and been doing that ever since. And I had such a good time there. I ended up being a mentor and leading that mentorship program for a while. And now I'm at a company called Zorro, which is a large e-commerce company selling primarily to small and medium-sized businesses. And it's a subsidiary of Granger, and liking it there. So, yeah.
So I know this is a Python meetup, but besides Python, what's your favorite programming language? We celebrate all languages here. So
Day to day, I pretty much only use Python, but Scala is probably my favorite non-Python language because it seems to get a lot of the syntactic sugar of Python with kind of the power of a JVM-based language. So there's some cool things that exist in Scala that you either don't need to think about directly, or we just don't have in Python. So love that language.
Yeah, Scala is pretty awesome. The Scala's match style statement is coming in Python 3.10. It seems like maybe I'm looking forward to that.
Yeah, definitely.
So without further ado, why don't we get your screen shared, and you can take it. You can start your talk.
Great. So for those of you who didn't have a chance to see, today we're going to be talking about production-ready machine learning. Before I jump into things, I did want to, do my promised announcement that Zorro is hiring, and I really do like it there. So I would suggest everyone to chat with me afterwards if you're interested in making a career change. We're hiring data scientists, data engineers, software engineers, DevOps, analysts, pretty much everything. And yeah, loving my time at Zorro so far. If you want to chat with me after this or check out some of my other stuff, I do have a blog at zackrosenberg.com. A decent amount of code up on GitHub that's public at Zaxer, or ZAXR on ChiPy Slack as well for questions after this is over. So this talk today is going to be about, despite machine learning being faster and easier than ever, it remains true that machine learning models, most of them don't make it to production. And the question is why? And that's the topic of tonight's talk. Production-ready machine learning is about more than just having a good model that you can validate and that works well, and more than just the code quality. It's about a lot of other things, and that's kind of the focus of tonight, the full machine learning lifecycle, how MLOps can help with making things production-ready quickly and easily, and why it's important to any place that's going to do, any business that's going to be doing data science. Also going to talk a little bit about how not to just build MLOps infrastructure, but to design it in a user-friendly way, and using open source tools, and ideally, other than maybe some cloud infrastructure, pretty cheap or free. So because this talk is designed to be friendly, we're going to take a step all the way back and talk about what machine learning processes typically look like. So here's one example, just a diagram I pulled off the web. A typical machine learning process will start with some raw data, will involve a lot of cleaning up of that data, and then engineering features that work well with the model. Splitting your data set into two pieces, the data that you train your model with and a little bit of a holdout piece of data so you can make sure your model actually worked with a separate data set. And maybe along the way, you also tune the model. So what that means is you're not just going to train one model, you're actually going to train a number of variations of the same model or multiple models and see which one works out best. And you're going to evaluate how your model performed based on that data you held out. Assuming that you have a model that's better than your previous one, based on some metric that you choose, or you've met some minimum threshold that ideally you've decided in advance for a project. What you have here is a quote unquote final model that you can start using, even though there's really no such thing as a final model. The reason I really like this diagram is it shows that despite machine learning being having a ton of blog posts and being very interesting, the machine learning part of it and the work for data scientists is mostly related to data. Cleaning up that data and engineering that data takes about 80% of the effort on a project. I find that this rough ballpark is pretty true. And with the proliferation of pre-trained models and libraries that have implemented a number of pretty advanced techniques, the actual writing of machine learning code is pretty minimal. You can sometimes use models in just a few lines of code in Python. Here's another view of a machine learning process. So pretty similar, this kind of modeling section that you see up top. And pretty similar, once we have a model, we're going to use it to make some predictions, whether that be in batch or providing a service where people can interact with your model to get real-time predictions. And maybe maybe things don't end there, extending this a little bit, maybe we have some high confidence and low confidence predictions that come out of our model. And if we're not really sure that our predictions are good, maybe we have a human in the loop process where we ask a domain expert, a human, to actually label some data, which we can use in our next round of training the model to help improve it, to be able to address those low confidence predictions for future models. One last look, again, looks pretty similar, but it extends the workflow a little bit more. So after we're done doing predictions, we want to monitor our predictions and make sure that our model's still performing as well as we think it should. Inevitably, models degrade over time for a number of reasons. So the question is just how long will it take and how bad will it be, and what do we do in response? So a full ML lifecycle doesn't end with just tossing a model out there and making predictions. It includes monitoring the performance of that model and either automatically or with human data scientist intervention, making improvements, tweaks, or retraining of the model and kind of going through this whole process again. So I think I've made it pretty clear that the machine learning code at this point is, not a lot of the actual work that's involved here. And depending on how much of the life cycle you're completing, there's a lot of other components that are potentially pretty challenging. So this diagram, for those of you in data science or MLOps, have probably seen this a million times by now. It's from a paper called Hidden Technical Debt in Machine Learning Systems. And it talks about at Google and other large companies, when you maintain models for a number of years, what are the other problems that you see and other important components in the process? And you'll see that how you serve your model, how you monitor things, how you configure it, all of the data cleanup and extraction and collection, that's where a lot of the real work comes in here. And I don't mean to belittle the machine learning part of it. I am a data scientist after all. It's definitely thought-provoking work and requires quite a bit of expertise. But as far as effort, a lot of this stuff is more impactful than people give it credit for. And that's what we're going to talk about today. So MLOps gives us a way to address that. So MLOps, pretty simply, is just is helping us automate the machine learning process all the way from the beginning of collecting our data through monitoring the outputs of our models, and around we go. And as you probably can guess from the name, machine learning ops, this is a cross-disciplinary field. So it includes obviously the machine learning part, but it also includes ops, which we get from DevOps and data ops. And there's really a lot that goes on here. So if I were to put it into an equation like you see here, I would say that MLOps is DevOps, or CI, continuous integration and continuous deployment, plus data engineering, plus continuously training your model and having infrastructure to do that, and being able to monitor your performance of your model as well. So why do we need MLOps? So if you're a data scientist, you can develop your model, but the question is, what do you do with it when you're quote unquote done? And how do you make sure that along the way you have the resources that you need to be able to train that model effectively? So MLOps is important because it can help us fast track work and let data scientists focus on the things that generally they're hired to do and have the most proficiency with, which is data science and sometimes building machine learning models. So if we have infrastructure in place that can take all of those other complex things out of the equation by automating them wherever possible, you can spend more time as a data scientist focusing on the actual models. And that can accelerate the development of models and the deployment to production by weeks at a typical company. It also helps improve your customer's experience. And when I say customer, maybe you're an e-commerce company like Zorro, where those are kind of the audience for your models. But it could also be your internal customers, other folks within non-technical folks within your company who are using the outputs of your models or something like that. And by giving data scientists access to infrastructure and automation that can help them do their jobs more easily without having to think about all the tangential parts of building a machine learning model. It also frees up data scientists not just to work faster, but to start using cutting edge techniques that otherwise might not have been on the table. For example, if you want to try out a cutting edge NLP, a natural language processing model, if you were working on your local laptop, that probably wasn't going to be an option to train. And if so, it might have taken weeks or months to actually train that model and frozen up your computer that entire time. So having infrastructure ideally in the cloud that's kind of automatically there and easy to spin up as part of this MLOps process can help data scientists do some cutting edge work. It also helps provide transparency. So part of MLOps is providing not part of the infrastructure is also providing visibility to other folks, sometimes non-technical folks within your company, so they can interact with your models in an easy way. So that transparency can help domain experts make better decisions with your models. So what does that actually mean in practice? So a company that implements MLOps or has some kind of infrastructure or platform, you can take things like deploying a model to production from taking weeks to do and potentially being a one-off process that a data scientist might have to figure out, which probably isn't their area of expertise, to doing these things nearly automatically and in maybe 15 minutes. Scaling resources can go from, well, I only have my local laptop, or maybe I can spin up a single machine in the cloud, to making it nearly instantaneous to spin up as much resource as we want if you're using a cloud platform like AWS or Google or Azure. We also can avoid issues like having to reconcile environments. I've seen this at a lot of companies where a data scientist will build a machine learning model and then they hand that model off to somebody who's expected to make the code production ready, meaning sometimes even switching languages. Sometimes it's just taking something that was run on Windows and making sure it'll work on Linux and the right versions of libraries and things like that. At its simplest, reconciling the development environment with the production environment where you need it to run would typically take hours. It can take much longer than this. With the right MLOps workflow, we can make that pretty much instantaneous. And lastly, if you're working on models as a data scientist, locally or without kind of any infrastructure to work with, chances are you don't have a lot of lineage into the past versions of models that you've trained. Maybe you keep an Excel spreadsheet or a Google sheet where you track all of the different experiments that you've done for your model, and that lives somewhere. Maybe you're even good about tracking it. But what you probably don't have all the time is a full list of all the experiments that you've tried, the data that was used to train them, the times that they were trained, related metadata, how those models were used in productions, etc. So with MLOps, we can build a system that will give us full traceability into all of our experimentation as well, which is valuable not only for the data scientists working on the project, but for a whole business. So when we think about designing a system that can do all of those great things for us, what are we interested in from an architecture point of view? So reliability is a must. If I can reliably train a model on my local computer, but I try and use some MLOps infrastructure in the cloud to do it, and it fails 20% of the time, well, I'm probably not going to use that system. And it's not going to help us when it comes time to go to production. 20% downtime is not acceptable. So we need a system that's reliable. We also want something that's going to scale not only with the resources we might use for a single model, but with any number of models we might develop. If we free up data scientists' time so that they can focus on more problems and building more models, we want to make sure that there's a scale to support all of those. So we're going to want to support many projects with a lot of CPUs, a lot of RAM, maybe even GPU support. And on the prediction side of things, we might want to serve our model so that a lot of people can interact with it on the web. Maybe that'll be thousands or even millions of people interacting, making requests for predictions from our model. So we need that kind of scalability. This one is a little subjective. I think portability is really important. So I've been at companies in the past where they say, hey, we're changing from AWS to Google Cloud, for example. And, at my pay grade, it was never really had a say. So if you build an MLOps infrastructure and architecture that only works with, say, SageMaker on AWS, and your company decides to switch away from Amazon, well, you're in trouble. It can also save you a lot of money if you're using open source tools and other free tools instead of paying for really expensive platforms. And lastly, and one of the most important things in my experience that I don't hear talked about nearly enough is making a user-friendly system. I saw a Medium post about a researcher who interviewed 100 folks who have MLOps infrastructure and asked them what the pain points were. And almost all of them said that they didn't like their system because they weren't intuitive and they were hard to work with, which is shocking that pretty much all of the people interviewed said the same thing. So we'll talk about user-friendly design from a few different facets, but I'm going to talk about a few things that I've found important in interviews with folks at my companies I've found important. But I think the most important thing is here, if you want user-friendly design, you have to listen to your users. That sounds like common sense, and yet somehow does not happen a lot of the time. That doesn't mean build exactly what your users tell you they want. It means listen to their feedback and prioritize things that will help minimize their pain points with the system. More important than just building a good system that's going to be friendly for users, you can build the best system in the world, but if you don't get users to adopt your system, well, what was the point? So we're going to talk a little bit later about how to get users to adopt your system, but user-friendly design goes a long way in helping that happen. So things that I've found that are important and that are important to me is that as a data scientist, I want to do as little configuration as possible, as little clicking as possible. I want to learn about process and the specific tools that I need to use on a day-to-day, and not all of the implementation details under the hood. And also, I don't want to have to do work for every new model I make to repeat the same workflow. We saw on a few past slides, the machine learning lifecycle looks pretty similar for most of the models you're going to see. So user-friendly design to me says, can we generalize the workflow to help with the minimization of configuration and extra files? So to make some of these things more concrete from an architecture point of view, this is what I've been talking about kind of at a high level. This is what an MLOPS architecture could look like. This is something I put together. You'll see a bunch of these diagrams on the web. This is meant to capture the infrastructure and the architecture that goes along with a complete machine learning lifecycle. So looking at this middle row, you'll see we start from a code repo, and you should be version controlling all your code. I think that's important to say because I know a lot of one-off experiments or SQL queries or exploratory data analysis and notebooks oftentimes don't make it to version control. So version control everything. That's hugely important to workflows in general, even before getting into MLOps. We're also going to want CI/CD. That's important for anything in the software space. You want a good way to make sure you're always running unit tests. Yes, those are important in data science as well. Integration tests and deploying Docker images that I'll talk about in a bit. The meatiest part of this though is being able to train models via a pipeline, ideally somewhere in the cloud, and making this automatic and easy to do. Other components of the infrastructure that come a little bit later are things like, having a place to store your models in a model registry where you can easily decide which ones should go into production or not, and interact with them later and have lineage to them. Once you've trained your models and you have them stored well, we want to serve those so that we can make predictions in whatever environment we're trying to use them in. And whenever you have a service from the software engineering side, you definitely want application performance monitoring. You want to make sure that your system doesn't go down. But we're also going to need in data science land something that's a little bit special here. We're going to need model performance monitoring, which is something very different from this application performance monitoring. And up here, which I'm not really going to talk about today, are kind of the data components that go into this. As important as data is, oftentimes the folks that handle this will be on a different team. So I'm not going to talk about it as much at the moment, but the idea is that if you're going to train a model, you need data. Sometimes you have batch data, or sometimes you have real-time data, and that data will have to be transformed in some way, stored in a way where it's easy for access from a model training point of view. And also, when it comes time to serving the model, especially if it's in real time, can we serve it performantly? And can we make sure that all of this data is being monitoring to make sure something doesn't go wrong? Because machine learning models are garbage in, garbage out. If all of a sudden there's a breakdown in your data flowing into your model, it is not going to perform. High level, the unfortunate part, I showed that diagram, looked like everything was connected and great. MLOps is a pretty new and emerging field in just the past few years. So unfortunately, there are not really many end-to-end solutions. On Amazon, there's SageMaker, and new for Google, there's Vertex, which combines a bunch of technologies. They're pretty early days at this point. So, and they're also obviously proprietary and restricted to their platforms. So chances are, when you're building a system, you're going to be putting multiple pieces together, multiple different technologies, whether they're third-party ones, open source ones or not, or you build them yourselves. So my pro tip here is build modularly. I think that's a good thing for any architecture, for any system, but I think it's particularly important where the industry is at for MLOps today. When I'm choosing tools to fill those different slots from that last diagram, I like to choose tools that have large communities and strong documentation. There's nothing worse than picking a tool and then not being able to figure out how it works because there's no documentation or anyone you can ask about it, and spending hours and hours and hours digging through source code, which chances are aren't even in a language you know, which is just not fun. No matter who you are listening to this, if you're a data scientist thinking about how you can improve your workflow by setting some of this stuff up, or if you're a dedicated MLOps professional, or if you're just someone else in software engineering or data engineering or DevOps roles, to make this happen takes a lot of different types of expertise. So everyone should work together. I'm a data scientist on a data science team. Companies I've worked at, we have separate software engineering teams, data engineering teams, DevOps teams. This type of system can't really be built and maintained without all of those different areas of expertise. So work together. Lastly, when picking tools, make sure that auth and passing arguments is straightforward and will work for your use case. That sounds really basic, although I think a lot of people on this call will know that it's painful, but you would be surprised how much of a limiting factor this is in a lot of the tools that are out there in today's day and age. So when you're actually thinking about tools that you want to use, there's this link, MLOps.toys, that I found out about recently, which is just a curated list of MLOps specific tools and which kind of slot in that last diagram they fill. I suggest checking this out. It has a pretty good list and some pros and cons for each tool. But with that, enough background and pontificating. I'm going to walk through a real example with real tools. And before I jump in, these are not any tools that I necessarily recommend that you use. I selected tools to show today that are really commonly used at companies. So you should always start this journey into MLOps, I think, with tools that you already have available to you. It's going to make your life easier. You might not have tools that can actually accomplish the goals of that architecture diagram back that, but I think you'd be surprised how many tools you already will have at your disposal. So I'm just going to show some popular ones here for this example. In the interest of time, since we're already something like 30 minutes in, I'm not going to focus on the data parts. I'm not going to focus on serving models. I'm just going to focus on how can we get an experimentation pipeline going so that if I'm a data scientist working, I can just commit my code up into Bitbucket or GitHub or my Git repo and have it automatically run my unit tests, build my images, train my models, and store those models and their metadata for me so that I don't have to figure out how to do that myself or be running it locally. So here are the tools that this this example is going to walk through. So I'm going to use Bitbucket Cloud. I think a lot of companies are on the Atlassian suite for Jira and things like that, so Bitbucket's pretty common. For standardization, I'm going to talk about using Cookie Cutter to create templates so you don't have to create new projects from scratch every time. For reproducibility and containerization, talk about a tool called Docker, which I think some folks will be familiar with. There are other containerization options, but Docker is pretty popular. For CI/CD, again, Jenkins, because it's popular. There's a lot of options out there. The infrastructure as code component, I'm not going to talk about very much, but if you're spinning up infrastructure, it's nice to be able to store that so that you can easily spin it up and tear it down using infrastructure as code, and Terraform's a popular tool for that. Pulumi is a similar one that's out there that I just found out about, which is pretty cool too. And then the meat of getting things to run in the cloud in particular, and orchestrating your workflows and training work are going to be Airflow and Kubernetes. Airflow is a general tool, so it's not machine learning specific, and Kubernetes is also a pretty general tool. And lastly, when we're doing all this, we want to keep track of all of our metadata and our assets, like our models and our evaluation and our hyperparameters. And we're going to use MLflow, which is an open source and popular Python library. I think they started in 2018 and is an open source project from Databricks. So I'm not going to dig in deep into any of these tools. That would take way too long, and there's plenty of good guides for all these things. What I'm going to talk about really quickly is what we're using them for. So Bitbucket, besides being used for our version control system, is also going to be used for GitOps. So what we're going to use this for is every time we commit code to our project's repo, we're going to trigger our CI/CD, our Jenkins pipeline, to automatically do things for us. And we can even set up different behavior based on different branches. So master branch might deploy to production, the develop branch might deploy to a staging or development space, and a pull request might be used for some testing purposes or for some staging areas as well. Cookie Cutter we're going to use to easily spin up new projects without having to copy and paste files and folders and delete things, and so that we can have a standard structure across our team of data scientists. Docker is going to help us avoid the "it works on my machine" issue, but it's also going to provide us a way to work in the same environment locally as we will in the cloud during development as we will in production. So it's not just works on my machine, it works on my machine in my various machines in development and my various machines in production. Jenkins for CI/CD. What that means from our point of view is we're going to use Jenkins to build a Docker image, run unit tests within that Docker image, which I think most folks don't bother running in a Docker image for their testing. And then we're going to use this to trigger our actual training process via an Airflow DAG. And Kubernetes is what's going to orchestrate our containers and allocate resources. And in this example I'm going to show, I picked Google Cloud because it's the one I'm most familiar with as where our resources are going to come from. So this is how that all kind of fits into the architecture. Up front, we're going to, we have Bitbucket, Docker, Cookie Cutter. Then we have our CI/CD with Jenkins. Then we have orchestration of our training with Airflow and Kubernetes. And then we have MLflow kind of behind the scenes, behind this training, keeping track of everything that we're doing for us. Walking through what the workflow might look like, this is a really specific implementation that goes along with those tools. So, first step would be committing to your Bitbucket repo. That will trigger a Jenkins pipeline. It'll build our Docker image. We'll run unit tests in that Docker image. Then we will optionally trigger our training process, because training can oftentimes be very expensive and resource intensive, and we don't necessarily want to train when we change the README. So I'll talk about how we can implement this decision point later. But once we trigger our training process, if we decide we want to, our typical pipeline will do all the things we showed in the first few slides, which is extract and QA our data, transform it, train our model, evaluate our model, and then a nice system will notify us when it's all done so we don't have to keep checking. Behind the scenes of this entire process over here in this training pipeline, MLflow will be keeping track of assets and metadata for us. And the back end of that, since I'm in Google Cloud Land, will get tossed on cloud storage and in BigQuery for the data warehouse component. And I'll skip the deployment and prediction parts for now, but you can refer to this slide later if you're interested to see how a complete flow might might work. So let's dig in even deeper on the engineering's point of view with these tools. And I'm going to show some real examples here. So these slides are available and I'll post them pretty much everywhere so that you don't have to like take screenshots of this stuff. But I wanted to show like what this could actually look like instead of continue to talk about it vaguely. So first I'm going to start with Cookie Cutter. So Cookie Cutter is a Python library that lets us template folders and files. So it's a very basic tool, but really powerful in that it lets us create all of our files and our folder structure exactly once for our standard project. And then whenever we want to create a new project, all we have to do is run one command line command for Cookie Cutter to automatically fill in and substitute values for the parts that we want to change from project to project. So right here in these double curly braces, we'll substitute in our new repository name here. Within these files, you'll see these double curly braces as well to substitute in project name or resource usage or other things that we might want for our project. That's really important to help us write less boilerplate, but also so that we have having a consistent project structure aids understanding across projects, or even when you revisit your own project, or if you're working on a team with other folks, by just looking at this project and in my source folder down here, I see there's a train.py. If I knew nothing else about this and I didn't read the README, I would guess that this would train my model. And if every single project looks like that, I have a pretty good entry point to trying to get familiar with this code. Similar things with predict or with data or with a config file. You can obviously add on top of this, but I usually try and keep the core part of each project looking like this and adding other modules where they're necessary. Something that I also do is use the right tool. What I think is the right tool for the job. So notebooks to me are not a production tool, even though there's increasingly tools that will help take notebooks and toss them into production. I like using notebooks for exploratory data analysis and for presentation purposes, but I keep them relegated to the side and not in our core source as well over here. Next, we'll talk about Docker. So going to the last slide here, you'll see that there is a Docker file in here. There's a Jenkins file, since we'll use Jenkins, and a Docker compose file. And also this pipe configuration file that I'll talk about in the next few slides. So with Docker, this is what a standard Docker file might look like for Python. Forgive the old version of Python. This is what I had handy. I use the official Python Docker image in a slim version to try and keep it a little bit small. I install what's in my requirements file with pinned versions. I strongly suggest pinned versions if you don't want surprises. And to go with our previous project structure, I make sure our working directory is that source folder. And then you might not have noticed, but there was also a script called runscript.shell. That's just our entry point. That basically just runs train.py, for example. There was also a Docker compose file in there. And Docker compose here, I'm using it a little bit differently in this example. The goal here is to get us some of those user-friendly local development things going on. So Docker compose is used often for application development to spin up a bunch of different services all at the same time and make sure they're networked together and things like that. Here is a trick that I learned from my last boss when I was at Spins, where you can use services basically as ways of just not requiring your data scientists to write Docker commands at the command line and have to learn too much about Docker. Instead, you can bundle all of the commands that they might want to run in a pre-written file. So you can just run Docker compose run and then a service name, and that includes all of the configuration like mounting volumes and credentials and environment variables and working directory and things like that. So there's more that I will typically use, but two common ones are run script, which is just running a Python script, just how you would normally Python run it, but in our Docker environment. So that's key, because now we're developing and running our scripts and testing things in the exact same environment that we're going to be using when we go to production. So if we've been running our tests in this environment all along, deploying to production is going to be easy. There's not going to need to be a whole new layer of converting stuff. There's also an IPython shell environment, or there might be a Jupyter Notebook environment, so that when you're running your Jupyter Notebooks, you still want that to be in the same environment that you're going to be using for production. So this makes sure, again, you're using the same environment. One handy little trick is to make sure that folks don't have to figure out credentials if you're working with resources in the cloud or other services you have to auth with. So we're using Google Cloud in this example. So one trick is just make a volume for Docker and mount in all of your, set this up exactly one time with all of the credentials that you need. So that way, once the developers, data scientists have set things up once on their computer, they never need to think about it again. So we've talked about our project structure, how we're going to be working in a Dockerized fashion locally and have that Docker file already in the project. Next, we're going to move on to Jenkins. So now our project, we've pushed our code up into our repo, and we want automatic CI/CD. So for that, you might use Jenkins as their multi-branch pipeline capability. So instead of having a pipeline for every single project, because these projects are all going to look the same if we're using the cookie cutter, we can have exactly one pipeline and reuse it all the time. That's really convenient. If we're hooking this up with Bitbucket, you can set up webhooks in Bitbucket that will trigger your Jenkins multi-branch pipeline. And then on Jenkins, it will actually do our Docker build, run our tests, and lastly, trigger Airflow. So this Airflow is what's actually going to allow us to do our training or predicting and things like that. In this case, this is an example function using Google's managed version of Airflow, which is called Composer. So just triggering a DAG here with some configuration specific to that Airflow run. Now, I said before, we don't want to train every single time we commit code because maybe you're just changing the README, for example, or maybe you're changing the prediction part of the code, which doesn't require retraining a model. One quick hack with these tools, and there's better ways to do this, sure, but a really quick hack for this might be Jenkins can decide whether or not it should trigger this DAG by looking at your Git commit messages for a flag that tells it to train. That's not probably the best system in the world, but I just wanted to show, how simply you can wire these things together if you're a little bit creative about it. Next, the real meat of this is Airflow and Kubernetes, and these tools are very complex and deep. And really, if you're going to be building a system with these tools, you might want to learn quite a bit about them. I picked these just because chances are, if your company already has, even if your data science team is new, if your company is already developing apps or doing data engineering in any way, they might already be using Airflow and Kubernetes as tools to help with that. So that's why I chose these for this hypothetical example we're walking through is, if you have these tools at your disposal and you have folks who are experts in them, absolutely use them. They might be general purpose. They might not be the very best thing for the job when it comes to MLOps, but they could get you 90% of the way there and in a fraction of the time. So in this case, how we'll set this up is because we're using a cloud environment, Google Composer will set up our Airflow and Kubernetes, but you can also manually install Kubernetes and Airflow into your cloud environment. So again, just remember, if you've got it, take advantage of what you already have. Leverage your company's existing setup instead of setting it up yourself, especially since cloud resources are not free, so no need to reinvent the wheel. When we actually run things in Airflow, because training can often take a lot of resources, maybe you need 16 CPUs and 64 gigs of RAM, maybe you need a monster GPU to run for a week. We're not necessarily going to use the same resources that Airflow is using. So we can use the Kubernetes pod operator to say, when we're doing our training, give that its own dedicated pod, maybe on its own dedicated node with its own dedicated resources at the scale that we're going to need. And Kubernetes and cloud will help you scale this pretty much to anything you can imagine at this point. So I said before, though, that we don't want to write a lot of configuration. Airflow, for most folks who have used it, you end up writing a DAG, a directed acyclic graph, or a Python file in this case, for every single workflow, every single project. But we've already said our machine learning workflow looks pretty similar every time. So rather than writing a DAG for every single project, only write it when it's necessary, and instead use a generalized DAG. So the way we can generalize DAGs in Airflow DAG runs have something called conf. It's specialized configuration or key value pairs that you can pass in a JSON snippet to each one of your DAG runs. What this would change in a DAG is instead of hard coding the image, the Docker image, for example, that you want your Kubernetes pod operator to look like, you can use, this actually uses Jinja 2 under the hood, just like our cookie cutter did. You can actually pass in dynamically the image that you want to use. And you can use the same thing for any other configuration you might want, like which script you want to run that will do your training. Maybe it's not train.py. Environment variables that you want to pass in specifically for that run, or other arguments or hyperparameters, things like that. So you can use the same common structure by basically turning this into a template. You can also pass information between tasks in Airflow with a tool called XCOM. It's not particularly user-friendly. It's a little more user-friendly in Airflow version 2. I'm still on version 1 when I use this, but that is the right way to pass things between tasks according to Airflow. And lastly, you can also use factory patterns or the trigger DAG run operator to make use of portions of other DAGs or reusing entire other DAGs as part of a new workflow. So if I have a bunch of tasks that indicate my training portion of my pipeline, I don't have to copy and paste those even if I make a new DAG that looks slightly different. I can use a factory to generate that portion of the pipeline and feed it into my new DAG. That's particularly important in data engineering as well as MLOps. When you have hundreds or thousands of DAGs that you're going to be working with, you want a really quick way to configure those, and you don't want to be writing them from scratch every single time. In this hypothetical system, in our repository, there was a pipe config.yaml and a .env, although I think my tree view didn't show the .dot files. This is where you would kind of configure, in this hypothetical example, how you'd pass information through to your training. So .env might have your hyperparameters, and pipe config, which is the pipeline configuration, might say, here's how much CPU and memory I need. That information will get pulled out of your repo into Jenkins, and Jenkins will pass that through to a training DAG. So when it comes time to spin up your image in a Kubernetes pod, it'll actually pass in those environment variables for your hyperparameters. You could also use arguments for this. That's either preference, or sometimes the tools just only have one choice or the other. So do whatever works best for you. There's no real right or wrong answer there. What I'll say about this system is it seems a little bit hacky at points, right? Like I just made these random files and I'm doing weird hacks to pass things through. That's because we're using general purpose tools. Jenkins and Airflow are as general as they get for their respective pieces of this pipeline. This is where more specific MLOPS tools shine. So instead of Airflow, there are tools like Kubeflow that are designed specifically for machine learning workflows and passing arguments for that type of work. Similarly, you'll find things for CI/CD that are more designed towards that, that are a little more modern than Jenkins, for example. So I just want to show what you can do with what you've got. But there are a lot of tools out there that'll do a better job. So that's as deep as I'm going to go into how we could set up this example with those tools that I was talking about. Please reach out to me if you have any questions about particulars. I'm happy to share little snippets here and there without giving away the secret sauce. But let's switch over to talking about the user point of view, because all that looked really complicated. But we want to make sure our user experience is nice and easy, and data scientists don't really have to think about this. So this is what it would look like using that system we just configured for a data scientist. So if I'm a data scientist, all I'll do is do a one-line command line thing to create a copy of my cookie cutter template. Now I have a new project. I will do some quick configuration in that pipe config.yaml. And when I say quick, I mean there could be like 3 or 4 lines in there, like who should get the notifications, how much memory do you need, how much do you need a GPU, how much CPU do you need, and something else maybe small and basic. That's it. That's the extent of the configuration. Next, locally, I'll create my Git repo. I'll do a git init. And I'll push all of my code to Bitbucket. So now I have a standard project structure. I already have my Docker file for my project, or at least the beginning one that I might want to tweak, and I'm ready to go. So I'll start developing locally, and I'll do that inside my Docker environment by taking advantage of that Docker compose that we showed. So I'll do Docker compose run IPython, and maybe I'll start working in IPython or a Jupyter notebook. And when I'm coding things, I'll already start saving stuff. I won't just like write it to a local file randomly on my computer. In the same one line that I would write something locally with Python, I can use MLflow here to write it to our standard cloud location and use our standard MLflow instance that I didn't talk too much about. So I'll already be writing stuff to the cloud. I'll already be working in a production environment. When I'm done with my changes, I'll just do a git commit. And if I decide I want to train my model, in my commit message, I'll put that -- train flag that we hacked together, and I'll push it up to the cloud. And that's it. Now, as a data scientist, I can sit back and relax. All this stuff's going to get built in the cloud. It's going to be tested. It's going to train, and it's going to notify me when it's done. So I don't have my computer frozen up while something gigantic is running. And I can just keep working. I can even work on a different variation of the model and test that as well at the same time, because we have a lot of cloud resources we can spin up. The only thing I'll add here is if you're the user of this, the quote unquote pro tips to be production ready. If you're installing libraries, make sure you pin your requirements as you develop. It's an unpleasant surprise later if a version has changed and something no longer works. When you're developing, make sure you're committing and pushing your code frequently. Nothing worse than trying a bunch of stuff out during the day and then losing it and having to redo it. So work in short-lived feature branches, commit, push, merge frequently. Don't let stuff sit until you have the model that you think is perfect for a month in a feature branch locally. Any incremental improvements you make, merge them. And lastly, save all of your one-off commands. If you're just fiddling around with the database and you're writing SQL queries, save them somewhere. Even if you just toss them in a notebook, maybe you'll never look at them again. But I find personally, I am almost always referring back to those snippets at some point. So save yourself some trouble and save them as you go. Great thing about that process I just showed is the user had to know pretty much nothing about these tools. They had to know enough about Cookie Cutter to run one line, which you can have documented for them and they can copy paste. Docker, unless you needed to really customize your environment, Docker was set up for you, and so was Docker Compose. You just need to know how to run one command. Bitbucket, you only need to know as much about that and Git as you would for whatever your company's workflow is for Git, which can be pretty minimal. Jenkins, other than knowing how to read the UI in case your unit tests fail, you pretty much don't need to know how that works. And for Airflow and Kubernetes, similarly, you just need to know how to read the UI and check out the logs. You don't really need to know how those tools work, no matter how complex they are. So with that, I think we have some kind of system. We used what we had available, and it's pretty user-friendly as far as configuration goes, at least. But remember, we want to ask our users what they think, and just because we have built a tool doesn't mean that folks are going to adopt it. So at the very beginning of our system lifecycle, and you can find a million versions of this diagram everywhere on the web. I made my own here because it's slightly tweaked. But first, listen and identify what the problems are you're trying to solve, design a solution for that, and build it and document it. Document here, I didn't talk about before, is key. You can have the best system in the world, the best library in the world, and code might be to some degree self-documenting. If you don't write basic documentation on how to use it, no one is going to use it. Just that's how it is. It doesn't matter how experienced a developer they are. Most people don't bother digging into source code deep to use a tool. They just pick a tool where they don't have to do that, myself included, when I can avoid it. So document, document, document. Now we have a great system, and we did exactly what our users wanted, but that doesn't mean we're done there. So now you have to get out there and educate your users and advocate for the use of the tool. And if you've built something that solves the problems of these users, that should be pretty easy. And if you made it user-friendly, it shouldn't take a long time to help them figure out how to use the system. But go out there, do a demo, talk to people, talk to the potential users, talk to other people who are in your company. Just advocate for this process. If you want MLOps, even though I think we've made a good case for why it's important, a lot of companies don't realize yet that it's important, especially if you're on a small or emerging data science team. So advocate, 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 and socialize your ideas as well. So, social networks are great at sharing, spreading information. Hopefully that's good information and not misinformation, but take advantage of of networks within your organization to spread information about this. And lastly, just because you've built the system does not mean you're done. You have to maintain it, make sure it's working well, and support your users. And you will inevitably find that there's room for enhancement. Machine learning is complex, and even though one size fits most, the stuff that doesn't fit can be very, very, very complicated. So make sure you continue to listen, support, and iterate on the design. So with that, our too long didn't read here is, if you want your machine learning models to make it into production, you need more than just model and code quality. You need infrastructure and systems in place that can accelerate your process. And since many machine learning processes look similar, we can set this up in a pretty streamlined fashion using MLOps. We can use standardization, pre-built infrastructure, and automation to make sure our models can be developed quickly and get them to production without any hassle. And we can leverage tools that our companies are already using without reinventing the wheel, as long as we understand that we're going to need to work with other teams, because MLOps is inherently cross-functional. And lastly, MLOps, when you're working on it, should be user-friendly if you want it to actually make things more efficient, if you want people to use it, and if you're the data scientist using your work here, just for your own quality of life. So with that, I know I went a little bit long, but happy to take any questions that folks have.
Yeah, thank you very much. Everyone give Zack a round of applause in the chat. That was a really interesting talk, and something that's interesting to me, because I enjoy that type of stuff as well. We have a question in the chat. I think you kind of touched on this, but like maybe you can expand a little bit on like are there any best practices for version controlling Jupyter notebooks? I know you mentioned that you didn't prefer using Jupyter notebooks, so maybe you can expand on that, like why you don't think Jupyter notebooks is like the tool for that.
There is a fantastic talk about why Jupyter notebooks aren't always the right tool. So I will say Jupyter notebooks are fantastic. It's a great tool. I personally use IPython shell a lot, which underlies Jupyter notebooks. So I think it's about using the right tool for the job. So Jupyter notebooks are great for visualizing, creating presentations, and experimenting early on in a project, but they're very hard to just dump into production. There's a lot about them that are not designed for working with other tools well, or including version control for that matter. And so there's been a lot of tools that have come around, that have been built around Jupyter notebooks to make that all happen. And our host Joe knows more about that certainly than I do, because you do that a heck of a lot more than me. So I haven't, there are tools though, open source tools that can help you version control notebooks in kind of a readable way, so you don't just have this HTML junk when you're trying to do a diff, for example. In our case, since we use it pretty much just for exploratory data analysis and things like that, we haven't, the companies I've been at, we haven't really made much of an effort to put tooling around that because it hasn't been necessary. I think the version controlling for Jupyter notebooks becomes a lot more important if you're trying to take those notebooks and use them as kind of a run book in production for work that you're doing, whether that's an actual machine learning model, or at a lot of companies I'm aware of, as a way to run analysis for companies that don't have a broader analytics team or dashboards or things like that set up for them.
Great, yeah, thank you. I have a quick question. Like, so when you were showing the cookie cutter project that you was as a basis for your developer experience, your end user experience, does that get run as a single task in Airflow, or does Airflow run, like, does Airflow build that Docker image that was defined there and then run that code as a single task in your test?
Yeah. So what'll happen locally for cookie cutter, the developer on their local computer will actually create the clone of that cookie cutter template and commit it to their repo, and it comes with a pre-built Docker image, which you can set a reasonable default that might work for most. Maybe the latest version of Python that supports data science libraries, which is unfortunately usually a couple version behind the true latest. But to automate the use of all those files that exist in there, yeah, Jenkins will actually do the Docker build and push that. If you're using a a Docker repository in the cloud, it'll actually push that up there as well. So in this case, this is all in Google ecosystem, so that would be container registry, but it could be Docker Hub or things like that. And then, you can use that in any other environment when you make it to production. Does that answer your question?
Yeah, yeah. And so I guess, do you have like so you have a distinction between when your developers are working on something to like testing and experimenting, like maybe beyond local development? Do you have like a distinction between like kind of a test and a production, like, so once they've tuned their workflow and their model, then they make it into production, or once you push code, it automatically gets deployed to production?
Yeah, so I think generally giving one person the ability to deploy things to production is not a great idea. So what the workflow will help you do, as I described it in this example, is just it'll help you experiment quickly and train those models and put them somewhere, like your model registry. Actually deploying to production and even getting your code merged all the way through should have proper controls. So, companies I've worked at, it's good practice to have peers, especially in the data science area, review your code and your logic, have meetings around if your approach makes sense and if the validation is good. But when it comes time to deploy to production, the idea is the model can make it to a model registry, kind of a staging area for the models. And someone will eventually have to have the authority to go click and deploy that to production, but it should involve multiple decision makers along the way to make sure that it's warranted. And in any production system with machine learning, I would advocate for not only can you get that model into production, but you have failovers and backups for if that model is not going to work in production or if it degrades, because identifying issues with a machine learning model, no matter how much automation you have, requires a lot of statistical and machine learning expertise, and you're not going to do it in a half hour at 2 a.m. when you're on call. It's going to take probably, if there's a major problem with the design or the world changes, that could take days or weeks to redesign. So make sure you have failovers for data science, especially.
Well, again, thank you for your talk. That was excellent. I don't see any other questions. So before we end your talk, is there any calls to action you have for the community beyond what you've said already?
I would reiterate one part, which is if you are a data scientist at a company, or you're at a company with data science, make sure that you do what you can to implement some best practices. So it's things like version control and using Docker. Forget all of, even all of the more advanced infrastructure I talked about. You'd be surprised, I think, in companies I've worked at, and a lot of folks I know are working at companies that are not using version control or Docker or writing any kind of testing. Like, even if you take nothing else away from the rest of this talk, do that. It'll make your lives better and easier, and all of the other people who have to work with you if you're the data scientist, if you're doing those things. So that is my biggest call to action for, I think data scientists, we think of ourselves apart from other software developers and engineers in general. And there are reasons why that's true and why data science is different. But there's a lot of core software engineering practices that apply to anyone in any technical role, kind of regardless of your title. So I encourage everybody to learn about those and implement them if they don't exist at your company. You'd be surprised how receptive people are to making those types of changes. Last thing too is all of these slides I'm going to post in ChiPy Slack in a bunch of different channels, so they'll be available. But if not, reach out to me at ZAXR in ChiPy Slack, and I'm happy to share.
Well, thank you very much again. Great talk and great topic. So really appreciate your spending time with us today. And with that, I'm going to call like a 2-minute break before we move on to our next talk. So get another cup of coffee. Maybe it's too late for coffee. And see you just in a minute or two. I'm muted. Oopsies. I said, welcome back. I'd like to introduce to you Manaswita, has another excellent talk for us. And before we get started with that, though, Manaswita, why don't you tell us a little bit about your background in tech?
Yeah, hi Joe. So hi everyone. So my name is Manaswita and I am based out of Chennai, India. And right now I'm working as an associate software engineer at Navis LLC. So for the people who don't know, Navis actually delivers the industry's premier software system and applications for optimizing the terminal operations. So we have our own TOS, terminal operating system, which is called N4. And we basically work in the cargo supply chain. As for my role, I am working with Navis as a data engineer, and I am in the data engineering team, and it has been good 8 months at Navis. So 6 months internship, 2 months as a full-time. So yeah,
Great.
that's it.
How did you get into Python?
Yeah, so it was back in my college days when I was in my third year. I started working on a project with a company as an intern, and that is when I got to know about Python as a language. Luckily, I had a very nice mentor who had guided me into data science pretty much early on. So I learned the nits and grits about Python from him, and then there on, since I'm a computer science student, it was natural I picked up on Python language. Yeah.
Right. And besides Python, what's your other favorite languages?
Yeah, so favorite languages apart from human language in which we talk, it'll be Java because it has strong community support. The documentation is excellent and it is comparatively faster than Python. And also the industry level support for Java is really good. So yeah, Java.
Great. Well, I'm looking forward to your talk. So without further ado, why don't you maybe get your screen, we'll share your screen and we can get started. All right.
Okay.
Here we go. All right, take it away.
So hi everyone. So as Zack has covered pretty much everything about MLOps in the previous presentation, so this talk is going to be a slight more beginner version of that, and we'll be talking about a case study related to data science, visualization, and models. So for a minute over here, let's think that we are all a part of a company, and our company is growing and exploring and entering into numerous domains. And as a result, we need to hire more people. So we need to engage with more people, and we need to have a good employee base. So we start with hiring. So we start hiring people, and these employees, we run the organization. So we start hiring, and let's see what happens next. We start with a traditional hiring. We conduct interviews, conduct coding tests if it is a software engineering role, and then when we actually have these people with us, we spend time in training them. We spend a lot of cost is involved, in making sure that they are well versed, and a lot of resources and time of the other employees are also involved in making sure that these people are perfect and ready to work. But as soon as their probation period is over, or 1 or 2 years down the lane, we see that the people start leaving. And as a person in HR, you would see that although this talent acquisition was a greater challenge, what is even more big as a challenge is understanding why people are leaving. Because you spend money and development and everything else, time, resource on training these people, but slowly and steadily people start to leave. At this point of the time, as an organization, it becomes so difficult for you to see, that people are leaving. So that is actually termed, there's a word for it, and it is called employee attrition. So before you start hiring people, it is really important to understand and to see that a person who you are hiring is actually a right fit for your company, or whether or not that person will actually work for the company upon finishing of the training. So not only will it help the management to make more optimized decisions, but will also help to reduce the efforts in training the people. So what happens next is we got to the problem, but we need to find a solution to it, right? So our company decides to hire a data scientist at this point of the time. So let's say that we have hired a data scientist over here, and how is this data scientist going to help us? So beginning with Python. So a data scientist will have a lot of prerequisite knowledge about, let's say, Python. There can be other languages as well. So once they start with their task of collecting data, pre-processing data, cleaning data, and the data over here can be collected from the company itself, or there are some sources which like IBM has made their data set publicly available, but it'll be much better if the data scientist professional hired for the company starts collecting the data internally. And once when they have collected the data, they will first begin by understanding that what are those features in our data which are going to help us to see this employee attrition problem. So the data can be the data can have a lot of problem. There is requirement for you to pre-process this data. So your data can be categorical, that is, it can have both nominal and ordinal values, and hence it is necessary for a data scientist to encode this categorical features. And for that, again, you will require a strong Python or any programming language prerequisite. Then there can be missing values in our data. So as you can have a little bit hint, we are actually working towards predictive analysis, and this missing data can prevent the prediction for some variables, and hence it is necessary to impute the values for such data. Although there are various techniques available to handle this missing values, we use mean, mode, median usually to handle the values. So once that is done, the third part in data preprocessing comes up with correlation index. So when you have a lot of features in your data set, which can be the gender, the age, the education, you need to see how these features are actually correlated to each other before you can see the effect of these features on our target variable. So yeah, a data scientist brings onto the table a lot of background knowledge on programming languages, on data modeling, pre-processing, feature engineering, data cleaning, and alongside that, they definitely do bring coffee to the table, because I guess I can speak for the most part of the engineers over here that without coffee, I don't think so half of the engineers function. So let's see what happens after that. The first challenge which you face as a data scientist, and especially working in the field of HR analysis, is, and the first question which usually comes up is, why are people leaving? What can be the reason? And in order to understand that, we will have to do something, right? How are you going to know why people are leaving? So the answer to that question lies in data. And in order to unpack this data, we are going to use exploratory data analysis. So exploratory data analysis can be done in various ways. And as a traditional data scientist, you can use various standard programming tools such as Python, Pandas. But as the technology advances, there were various libraries which were created to ease this process and to save a lot of time writing the repetitive code. So let us consider this use case about which we were talking about, the employees leaving. So you see, from our data, which was given to us, a data scientist will try and generate various graphs and try and implement these graphs. So from the first graph, which you can see on your screen, you can see that age is a very important factor in deciding if a person is going to leave or not. So from the graph on your right, you can see that age is very much distributed normally, and people who tend to leave company are usually younger. So from this graph, we have actually narrowed down a little bit on the reasons why people leave, by finding out that, yeah, age can be one of those factors which actually influence the target variable, which is whether the person leaves or not. Then on the next graph, you can see the percent salary hike. So another reason, actually, I was pretty much surprised when I was doing this process, and I realized that the median person salary hike is actually around 14, and percent salary hike, that is the increment which you get in your company, actually does not affect the attrition rate at all, which was pretty much surprising for me, because I thought people usually tend to shift because of these reasons, monetary reasons, but the data speaks against it. So yeah, so as we move ahead, the digger we deep in the data, the more we have a better understanding of the factors. So moving ahead, this is the third kind of a graph where you can see that over time, the rate at which, if people tend to work for longer duration of time, they usually try and shift companies. And although there can be some probability or some error rate over here, but for the major part, the data speaks that overtime in any kind of industry can lead to people shifting from that industry. Next graph over here, which was again very intuitive and very interesting for me to see, was because you see people who work in research and department seem to have very less attrition than the people who actually work in the sales team. So if we take in consideration the confidence interval, this difference could be just a result of chance. But yeah, it's amazing, right? That it is usually people from one team or department which tend to go for attrition or tend to change your companies. So yeah, I'm not going to bore you with all these graphs if you're thinking. Let us discuss about something more interesting. So yeah, if you remember, I mentioned earlier that a trained data scientist usually uses standard programming tool, but now there are various automated libraries which help you assist in this EDA. So there is one is SweetWiz. So it is one of my favorite exploratory data analysis library. It is open source. It generates high density visualizations, and you just have to write 2 lines of code. And if you're someone who is not into programming a lot, this can be really helpful, right? You're just writing 2 lines of code, and the output itself is actually a self-contained HTML application. So you can easily integrate it with any of your already existing uh, architectures. The next one, let's pick up Pandas profiling. So Pandas profiling is a relatively easy to use, easy to set up standard Python library, and it is easily integratable with your favorite tools. So mostly people in data science like to use Jupyter and Colab, and there is extensive documentations available on how you can use Pandas profiling. Then we have data prep. So data prep is one of the fastest EDA tools in Python. It allows you to understand a data or pandas data frame with a very few lines of code in seconds. So yeah. The next we have detail. So kudos to the person who found the name, because it is interesting. It's quite creative. So detail is, in my opinion, one of the best EDA libraries out there. And I would say that because it outshines the others based on the level of customizations that are available within this library. In other words, it fulfills the purpose of EDA, since you can go deep and explore all the details in your database using detail library itself. And then the other library which we have is Dora, and probably you can search about it. It is, again, one very cool library available for automating EDA. So when this problem is answered, the problem of why people leaving, there comes the other challenge, that who are the people who are going to leave our company. So right before hiring a person, if we can make a decision if we should hire this person or not, on the basis of the fact that whether they will leave or not, it will be really helpful, right? So if you are with me till now over here, you can understand that this process of whether a person will leave or not comes under classification. So in order to deal with this who is going to leave and whether or not should I hire this who, we will be using classification. So let us understand what actually classification algorithms are. So in a sense, classification algorithms are based on a basic concept. So you have the training data set, and you analyze this training data set. And on the basis of this training data set, you can predict a target class. So in a typical classification problem, there are target classes or the output classes. And these are the classes into which a data point is classified based on the features being considered. So in our case, the feature can be the gender, the overtime, the education level, and the department in which the person is working. So all these things can be the features, and we will try and classify a data point that is a person into the target, whether a person is leaving or not, on the basis of these features which are being considered. So the basic terms that are used in classification are the classifier, which is the algorithm which is used to map the input data to the target class. Apart from that, we have the classification model. So the classification model predicts the target class of a data point based on the classifier. And then we have the features. So the features is an attribute of the data point that allows the classifier to observe and classify. So in our case, we'll be classifying employees into two target, going whether if the person is going to stay or the person is going to leave on the basis of features such as education level, experience, gender, etc. These features are obtained from the data set. So we'll be using various classifiers like knife bias, KNN, cat boost, etc. So let us begin with some of them. So first, let us understand what knife bias is. So knife bias is a supervised learning algorithm, and it is based on Bayes' theorem. What naive bias basically does is it assumes that there is independence and equality among its features. So the algorithm is able to estimate all the parameters on the basis of a very small training data set. So if you want to use naive bias, or when should you use naive bias, is dependent slightly on the data set. So suppose you have a very small training data set, it is recommended that you can use knife bias, and these classifiers are known to be faster in comparison to the more sophisticated methods. Let's move to the next slide. So what you see over here is, what you see over here is the different functions. So if you look at the last function, this is the predict function, and it basically predicts the probability of the person leaving or not. So this probability is calculated on the basis of class probabilities. And now this class probabilities is nothing else, but it uses mean and standard deviation to calculate the class of the probability. And then actually, there can be various ways in which we can move ahead with naive bias. So there is Gaussian naive bias. There is, I guess, there is one more. I'm not remembering the name right now, but there are multiple ways of implementing this probability density function. And once this probability density function actually calculates the probability, we get the output of whether the person is going to leave or not. So next available algorithm for us for classification is KNN. So basically, although I mentioned that it is available for classification, but actually KNN algorithms can be used for both classification and regression, and it is a supervised algorithm. So a particular data point is classified on the basis of the majority votes of its nearest neighbors. And the algorithm is more advantageous when it comes to more noisy and larger data set, as this algorithm itself is able to handle the large data set easily. And even with its simplicity, the nearest neighbors, this algorithm has shown to be effective in classification and regression problems. Apart from that, it can also be used in hand digital writing and satellite image scenes. So one more thing with K nearest neighbor is, since it is non-parametric, it is often effective in classification contexts with when you have a very highly irregular decision boundary. So yeah, KNN is one of the simplest and most important classification algorithms in machine learning, and thus we can use it for our cause. Moving ahead, you can see this is how we implement KNN. So we use Euclidean distance to find the distance between the point, our data point, and the predicted output. And we loop through the data points to be classified. We create an array to store these distances. And once we have these distances between the data points, we sort the array and we preserve the index, keeping the first k data points together. So that is when we do the majority of the voting. So moving ahead, we have the next algorithm, which is random forest. So random forest uses central tendencies like mean and mode to classify a data set. And again, this algorithm can be used for both classification as well as regression. Multiple decision trees are created in this algorithm at the time of training and for classification. And the mode is the output. And for regression, the mean of the tree is the output. So the algorithm usually results in the highest accuracy, and this one can handle big data sets efficiently. So it often balances the data set automatically, and it has the methods for handling the missing data problem. A random forest is a meta estimator that uses averaging to increase predictive precision, and it controls overfitting by fitting a number of decision tree classifiers on different subsamples of the data set. So suppose if you set the bootstrap as true by default, then the subsample size is controlled by the parameter itself. Otherwise, the entire data set is used to construct each tree. So that is how we implement a random forest. Internally, a random forest basically uses Guinea index. All this piece of code, we don't have to write it. We do not have to reinvent the wheel. But as a data scientist, it is important for us to understand when and how exactly, when and in which situation should be using a particular classification algorithm. So there are options of using AWS, Azure to use these algorithms without without going through this code. But yeah, as I mentioned, it is important to know when to use which one. So next we have is the support vector machine. So SVMs, right? So SVM actually does classification tasks in a very interesting manner. So it generates a hyperplane which actually classifies the given data points into different groups of similar features. So basically, it will create a plane which will group the same points together. So these new data points are then assigned to, so whenever you provide a new data point to this model, so it will assign it to one of the already existing groups on the basis of similarity. So the algorithm is easily able to, so when should you use SVM? So this algorithm can easily handle high dimensional data with more efficiency as it uses training data as a subset for decision making. It is a traditional machine learning method, and it can be used to solve large data classification problems. It is especially useful for a multi-domain application in a big data context. And the support vector machine, on the other hand, it is mathematically complex and a little bit costly when it comes to computation. Um, the hyperplanes about which I was talking are nothing else but the judgmental boundaries which aid in the classification of the data points. So I hope you're clear that when can we actually use the support vector machine. So yeah, what you can see over here is that the two main functions in a support vector machine is to first calculate the cost gradient, and the second is to calculate the hinge loss. Yeah, so moving next, we have one of the most famous algorithms, which is XGBoost. So what is an XGBoost algorithm and when should you use it? XGBoost is an implementation of gradient boosting for faster and better performance. So what I'm trying to say over here is that suppose when you have a lot of unstructured data, which means that you have some data in the form of image or text, you can use this algorithm then to give you the best results. And XGBoost has actually evolved from decision trees to random forest, to gradient boosting, and finally to XGBoost itself. So apart from the normal classification problems, it can also be used to solve ranking, prediction, regression, and classifier problems. So it supports all the major languages such as Python, R, C++, and Java. So you can see that actually XGBoost is pretty much powerful. And the main feature of XGBoost is that it is an ensemble of learning algorithms that apply principle of actually boosting the weak learners, and that is done using gradient boostings. So these are little frills in the library since it is laser based on computing speed and model efficiency. Nonetheless, it has a range of specialized functions. So the model's implementation supports the functionality for scikit-learn and the R architecture, as well as additional ones such as regularization. As I mentioned, the decision trees in their most basic forms are easy to imagine and um, implement. But by developing insight for these generation, the if you have to understand these algorithms in detail, yeah, the tree-based algorithms can be actually difficult. So this is a basic, sorry, yeah, this is the basic structure of how you can actually implement or try and solve this attrition problem. So we take the input data employee. So this can be either the company internally can collect the data of all the employees, which usually 75% of the companies do, preserve them in the database, and once you've done that, using various ETL pipelines, you start data preprocessing and data cleaning. So data preprocessing and data clean, after that is done, we start analyzing the data and we start using exploratory data analysis to find the data points which will help us understand those features or those factors which cause the attrition rate. And post that, when you have the data ready, we supply this data to the classification algorithms. As a part of this study, which I was doing, we can either use multiple classification algorithms and check the accuracy of each one, or you can go with the one which gave the best results, which for me was XGBoost. And once when you have this result, you can save the entire model as a pickle file and then use Flask or any of the Python-based tools to generate reports. These reports can be generated on any of the platforms, let's say Power BI or Tableau, and thus it can help you understand. And before you make policies, you can see that how should you retain these employees. Suppose that one of the factors is the age of the people, then how can you actually attract more young people into the company, and how can you tweak your policies on the basis of that? The second thing which we talked about was the overtime, and we can use again, the company itself, the HR policies can be implemented in a manner that we can, they can try and reduce the overtime as much as possible. So once this entire process is done, you will have two things in your hand as a company and as a data scientist. First, you will understand the reasons why people are leaving, and thus you can tweak your company's policies and make better policies. And second one, before hiring an employee, you can make a smarter decision based on this algorithm, on one of the classification algorithms, whether or not the person is going to stay. So yeah, moving ahead, as a part of the study which I was doing, there are all these different algorithms performed differently, and the AUC, that is the area under curve, for linear regression was around 0.71. For a naive bias, it was 0.66, 0.58 for KNN. So the value should be closest to 1 for a model which is doing really well. And SVM was again at 0.50, XGBoost at 0.78, and CatBoost at 0.77. So now here I would like to mention that all these accuracies were based on the model which was trained on my local GPU. Yeah, the my machine problem. And when we started working on this algorithm in detail, we realized that we can use AWS and Azure to actually enhance our own models. So yeah, that is pretty much important. And the best algorithm over here, which we found out, was XGBoost. So I'll be wrapping up by saying that understanding HR analysis and using models which can help you uh, improve the company quality life is really important. And that is how you can, this is just one of the use cases, and there can be multiple use cases like this where you can work ahead and ensure a better company culture by implementing them. So yeah, I guess that is it. And yeah, we'll be open to questions then.
Oh, thank you very much. If everyone could give Metaswit a round of applause, that was it was really interesting. To see Python used in different ways that I never considered before, and especially during this time, this the Great Resignation, as they call it, where everyone's leaving. It's interesting to know that people are doing studies on what those factors are. So there's one question in the chat. So for large data sets, how would you feel about using nearest neighbor to subset data into smaller, more manageable data sets and using naive Bayes against each subset?
Yeah, that makes sense. Actually, that's a very nice approach. And I wish I would have gotten this idea pretty much early on in my mind before jumping to another algorithm. So yeah, for larger data sets, I think so, because I have not implemented it. If we use nearest neighbors in the subset to train, and then for the other subset, if you use it to test, I am sure that the classification accuracy might increase. So yeah, sounds good.
And then, so I have a question for you. Like, how many features were you comparing when you were trying to determine, what features were most effective towards retaining people or having people leave, and how much data did you have like at your disposal?
So yeah, actually, I collected data from IBM and internally. So the features is actually included the age of the person, the gender, the number of times the person has actually changed their job previously, and post that, the level of education. So that was also a very important factor. One of the interesting conclusions was that the people who've done masters actually tend to not leave their company easily, and people with bachelors actually tend to leave. Another interesting factor was the distance from their home. So usually people who stay further away from home tend to switch jobs more often. I don't understand why that was happening. Maybe you can have an intuitive idea behind it, but people away from home actually change their jobs a lot. Another interesting factor was both male and female people. This is where gender equality is at place, tend to leave job at the same rate. So there's no myth that, okay, if you are a girl, you're going to stay, or if you're a guy, you're going to stay. It's equal. Both of them tend to leave their companies at the same rate. And another interesting factor was the city development index. So usually people who live in bigger and better cities tend to stay in their companies, and people from smaller cities actually try and shift to the other company. So my data set had around 14,000 data points, and yeah, these were all the features which were there, which were considered.
Very interesting. I guess for someone who's interested in doing something similar, like using, like, what would your advice to them to be getting started, to getting familiar with these algorithms and such?
Yeah, so when I pretty much started on these algorithms, I had no idea. So I would say that it is very important for a person to get their hands dirty with the code. So you start reading, first of all, reading and implementing research papers. And once when you do that, you will have an idea about how these algorithms are working. So I started with linear regression. Then I read the next paper, which was on decision trees and how decision trees are better than linear regression. Towards the end of my entire study, I made a table and I jotted down the points that why this algorithm is better, and what is it that is making this algorithm better, why linear regression is different from decision tree, why a decision tree is different from an SVM, how a boosting algorithm is actually ensemble boosting algorithm is bringing together two algorithm and boosting the weaker one. So yeah, that point, a lot of research. Yeah.
It's yeah, sounds like a lot of work, which is awesome. So before we end, do you have any like final calls to action for the Python community?
Yeah, it'll still be the same, that I know actually the machine learning aura has been created so much, but very few people actually get their hands dirty with the code. And it is really important for us to understand also the mathematics behind these models, because as you would have seen throughout the presentation, there is a lot of maths involved, right from probability, mean, median, statistics, to understand these ML models. So if your basics with mathematics are strong, you can actually understand these models in a better manner. So get your hands dirty with the code and understand the mathematics behind each of the models. That will be it.
Well, thank you very much. Really appreciate your being here and sharing your solutions to the HR problem of people leaving. And so I guess we're going to wrap up the meeting for tonight. And I'll see you later. But
thank you.
Oops, wrong person. There we go. Thank you all for joining us tonight. And if you'd like to stick around, we have an after party at the GatherTown, ChiPy.town. Let me bring that link up real quick. So http://chippy.town. If you want to come and hang out, that'd be great. But before we do, I'd like to say thank you to all of our speakers. Thank you to our sponsors, and thank you to you, our viewers, for coming and joining us. If you'd like to be updated on future Chippy events, feel free to check out our chippy.org or subscribe to the Chippy YouTube channel. We've got a lot of great content that comes out every month. So check us out. And until next time, I wish you a good evening.